My name is Leo. I'm a second-year PhD student at Penn State working under Dr. Xiaopeng Shen, working on hybrid machine learning physics models, differential modeling in particular. And I'm going to give you a bit of an overview, broad sense of some of the work I've been doing, kind of bring a bunch of different efforts in our groups and hopefully, in the broader community together. Great talks starting it off. I hope I can tie it up pretty well here. So just going to give you a little bit of an overview. I'm going to talk about the motivations of why we care about this, then the design of the framework, some impacts and applications using the framework, and then integrations into operational environments, which is ultimately our end goal here. So many of you may be already aware, the general idea of this framework is to embed or to join neural networks with process-based models and to do a number of different things. In particular, in our case, we were doing parameterization, so we work with physics models like HPV and SAXMA, PRMS, these rainfall runoff models, and we use a neural network like an LSTM to predict parameters for these models. But you can also do other things like predict missing processes and bias corrections and things like that. The reason we care is because we're able to get interpretability with these physical models and do predictions in extreme events quite well. We get indirect supervision by doing predictions on streamflow. We get GPU parallelism, and we get to generalize and extrapolate quite well again to those unseen events. Just to kind of wrap up that sort of part, I'm just comparing here a standard calibration, genetic calibration scheme to some of the parameters you might get with this parameterization network in our differential modeling framework. And you can see you get a lot of spatial coherence in the bottom graph with our differential HPV. And another thing we can get is this extrapolation to extreme events. So if we imagine this threshold in the black line is the peak streamflow our training data set is seen for these differential models, and potentially a data-driven model like just a pure LSTM. The pure LSTM doesn't necessarily reach the peak streamflow in this particular event, and that's because these are usually more like interpolators. By imposing some physical constraints, we can actually reach these peaks much more readily. So this is one more advantage when it comes to flood forecasting and getting these extreme events correct. And then the last sort of case, which is why we care about using these models, is because they're quite well performant compared to the model we hope to replace in the next few years, the National Water Model 3.0. So you can see just NSE here, we're comparing an NSE of 0.5 to 0.76 with our ensemble of these models. Why now we have this set of differential models. Why do we want a framework? Well, of course, we're in Cairo. We want to bring some research to operations, so there's some value in having a standardization. And this standardization in particular, to name a few examples, is important for NextGen, AWI's NextGen in a box, and also the river forecasting centers like Delfuse, for example, where these models need to be wrapped by a standardized wrapper like a BMI to make them operationally compliant. There's also an advantage to having the centralization because we can unify a bunch of different efforts across the community, of course within our own group, but hopefully also across the rest of the Cairo community as well, as these models potentially see more adoption. There's also just some advantage to having the standardization because it's very easy to iterate. So when we're going from, as Martin was talking about earlier with lumped and distributed modeling, there are advantages to having a framework set up for doing these sorts of models where only small refinements are needed to make big advancements in the style of modeling and so on. And the final point here is multi-modeling. So the standardization, again, and you'll see this in a bit, will allow us to create multiple model instances simultaneously, so we can do things like simple model averaging, but also more intelligent modeling, multi-modeling approaches, which I will show also in a second. But now that we have all that out of the way, let's just see what this framework sort of looks like. We call this DMG, but to just kind of simplify the outlook, just showing a basic setup for a differentiable model here. This is going to be doing parameterization. So again, we have a neural network. This is typically like an LSTM or a feed-forward network that is going to be predicting static and time dynamic parameters for a physical model. Again, this could be anything. It doesn't just have to be a rainfall runoff model. We have some ecosystem models. It could be a land surface model, anything of that sort. And then it's going to predict some output, and we can do a back propagation to train the weights of that network. Now, the idea of this framework is just a bit more of a generalization of that. So I know it looks a little bit complex, but the parts we really care about are highlighted here in red. So again, you can see the neural network and physical model parameterization. I'm just showing in the box on the right that we can do a bunch of these different models at the same time. And there's some generic framework set up here, so this is easy to do for different types of models and different types of neural networks. You can also update your, there's a trainer class that you can use to actually train these networks, and these are also configurable for different model types like lumped and distributed models. Your data pre-processing, all this stuff is generic and designed to be hot swappable. It's designed to be embarrassingly parallel, actually, so that we can do any type of modeling setup and really adapt as the developments in differential modeling and across different fields sort of come to fruition. And then finally, there's this model handler object in the center, and this is designed to be an immutable object that we can actually connect to these interfaces like BMI and also into like Delfuse, so that if we make a model like HBV BMI compliant, we could also make another differentiable model on like Saxma, for example, also BMI compliant without the extra effort of making a new adapter for it. So once you do the work once, the idea is that you don't have to do it again or with minimal effort. And so this makes it very easy to iterate and expand on the work you've already done. Another great thing about standardization. And so this has kind of come to fruition in the last couple of months in a more formal way with 2 different packages on GitHub. The first is this HydroDL2. This is just a bunch of physics models that have been made compliant with this framework in PyTorch and Python, so this is what we're working with in particular. And this is currently showing our HPV models both a lumped and a distributed style. But the DMG framework actually is also there, and these 2 work in concert to develop some of the benchmark models that we've come out with recently. And we'll also be holding some of our future work going forward. Excuse me. Yeah, so before I get into the operations, just want to kind of motivate, like what we've been doing with this framework, what's been possible with it. I like to think about this like dunes in the wind. The framework changes as the need arises, and so we've been able to do a bunch of different cool things with it. So it started with mainly the implementation of a distributed differentiable model, distributed HPV, which is, again, making predictions on the catchment scale. And we've done this on both the Merritt River Network and the CONUS Hydrofabric. And I'm just showing some examples of, like, we're able to do recharge on the seamless Hydrofabric River Network, and also we're able to do, like, streamflow predictions on that river network as well. And I'm not going to go too deep into the weeds here with these plots. I'm just trying to illustrate some of the work we've done. If you have questions or if you'd like to talk to me afterward, that's fine. We've also done this at an hourly resolution. So now we're doing hourly resolution distributed modeling on the entire Hydrofabric River Network. It's doing quite well, similarly to the daily model. And you can see that just looking at some extreme events here from 2018 in Texas, you can see the daily model doesn't quite capture the peaks of these streamflow events on these sub-daily events. So like an hourly model here does quite well capturing that. We've also done stuff on the global scale, so the same type of model, just applied on many more basins with Merritt, doing seamless simulations on almost 3 million catchments, so this is quite a bit larger. On large rivers, we see great performance. We've also been doing something recently with surrogate modeling, so this is diving into more of my research work. And the idea is that when you're doing predictions on very high resolutions in space and time, so hourly resolutions, say, on a global scale, or even just one or the other, these training times for your parameterization network can become quite large. So we're talking on the order of 3 to 3.5 weeks, which is okay if you do it once, but if you want to iterate and develop these models, that becomes quite time consuming. So the idea is when you're training a neural network, this parameterization network or otherwise, you can swap out your physics model with a surrogate. This could be an LSTM or some other type of neural operator, something to emulate the physics and then allow the parameterization network to learn accurately. And then when you want to go and do inference, you can just plop the physical model back in, and you get the same benefits of using the differentiable model with the physical constraints and so on. So yeah, just showing that there. Showing some comparisons using the solver on Streamflow. You can see, so like the idea with these solvers is you want them to be physically accurate to represent the sensitivities of your physical model. And so we're just showing here with the CDF that the blue line all the way on the right compared to the black line is the performance of our surrogate-based training compared to the process-based model-based training. So these actually can be quite promising for large-scale applications, giving 10 to 20x speed ups for the training. So this can be a huge case of improvement for the large-scale models. We've also been doing multi-model ensembles, like I was saying. We've done naive ensembles doing just averages with different differentiable models within our framework. So again, this has been with like SAXMA and PRMS and HBV. And we've also been doing some more intelligent ensembles with like a mixture of experts approach. So you can use like another neural network to learn how to dynamically ensemble models in both space and time. So this can give you some more improvements, not just in the general performance NSC, but also in the low and high flow performance of those models. So that performance is just shown in the pink compared to a collection of others, including an LSTM. We also been working on a few other things. I'm not going to go too much into the weeds with these, but foundation models, you can train a model, you can train like a parameterization network on a large set of data and inputs, including remote sensing data, the meteorology and gauges, and also static features, and then you can throw these into our framework and use those networks as parameterizers and hopefully gain the knowledge of more larger data sets. We have data assimilation, a variational data assimilation, also some AI-based simulation methods in development and review. And we also have a new kernel design we've been working on. So like I said, some of these models can be quite slow. On a lump scale, you can actually increase that speed by about 300x. And for distributed, it's a little bit slower, but still 5x. And we're able to bring down training times for those distributed models from 3.5 weeks to about 2 days. So there's a lot going on there. That'll be available very soon. Again, we can do this with different models. And then finally, I want to just jump right into the integration stuff with operations really quick. So over the last year and a half, we've been working with AWI quite heavily with Arpita, Quinn, Josh, and many others to bring these differentiable models, primarily the hourly model, into operational environments. So there's been a bunch of collaborations with them. I went and visited them in October last year to work directly with them on bringing this stuff into next-gen in a box, for example, and the next-gen ready data stream, or next-gen research data stream. Yeah, like as I was saying previously, this work has also been going into next-gen with ODP collaborating with us. And also the river forecasting centers. And the idea, again, is that we have this generic static interface, this model handler in our framework that will connect to like a basic model interface or some other standardization that allows us to communicate directly with our operational frameworks without having to make a new interface for every type of model we develop. And so that has resulted in another Python package, this DHBV2, which is actually going to next-gen and next-gen in a box right now, and they're being evaluated as we speak. So yeah, that's kind of just wrapping up some of this work. I know it's a little bit high-level overview, but yeah, I just want to give a little bit of motivation about why this exists, and hopefully bring some more people into this and unify some efforts across the collaboration. But I really am just honored to be here as like a student, but also being able to like collaborate with everyone here. Like Derek was saying, I feel a bit humbled by like everybody I meet here. 2 years ago, I never imagined I'd be in hydrology, let alone talking right here, right now. And I feel like the spirit of Cairo is honestly quite alive and well with the number of collaborations that have developed through all of this work and the number of people that have helped to bring it to fruition. I'm just a small piece, but I appreciate every single one of you that I've met, and hopefully we'll meet in the future. So with all that said, thank you very much. If you have any questions, feel free.